Today I'm going to talk about LeetCode question number 787, cheapest flights with K stops. So there are n cities connected by some number of flights. You're given an array flights where flights I at index I is equal to, from, to, and price, which indicates that there's a flight from city from and city to with a cost price. You're also given three integers, source, destination, and K. Return the cheapest price from source to destination with at most K stops. If there's no such route, return -1. Okay, so basically you have to find the cheapest flight or the smallest weight to get from source to destination. So here source would be here and destination would be here, but on the condition there can only be one stop in between. Okay, so if there was like another node here, basically if there is another node here, or what I mean is, so we cannot go this way because we have two stops in between. We can go this way, okay, and this just so happens with only one stop, this is the cheapest price. Okay, so how can we do this? When we think of shortest path with nodes, we think of Dijkstra's algorithm. But this won't work in this case because it's not flexible enough to take into account the k-1, or sorry, the k stops that we're allowed to at most have. Another algorithm we can consider is actually the Bellman-Ford algorithm. Okay, this algorithm is slightly slower than Dijkstra's algorithm, but it tends to be a bit more flexible. Bellman-Ford algorithm is good for edges with negative weights, calculating the shortest distance with edges of negative weights. Okay, and in this case, it's also good for calculating the cheapest price from source to destination with only k stops in between. Well, why is that? The original definition of a breadth, or original implementation of Bellman-Ford is basically what you do is for v-1, so for all nodes -1, and for all edges, okay, we calculate shortest distance to destination node. Okay, so this is kind of the high-level code implementation of Bellman-Ford, but instead of v-1, we're going to replace this with k+1. Why k+1? Because if we just, like in this example, we just use k, then it stops like right before our destination node. So we want k+1 for, if this is 1 here, 1, 2. Okay, so that's why we want k+1. That's how we're going to use Bellman-Ford here. So the runtime of this would be, originally for Bellman-Ford, it would be v times e, but here in this case it would be k times e. Okay, so that's how we're going to do it in this case. What other details of implementation? So we're also going to keep like a hash table of distances, or sorry, prices. Okay, and also in our Bellman-Ford algorithm, we're also going to keep a temp prices dictionary. Okay, so we're going to keep like a final prices dictionary and a temp prices dictionary, okay, in our Bellman-Ford algorithm. Okay, this is so because, you know, imagine we have like A, B, C here, and this is like 600 100, 200, and k equals 0. So obviously for prices, it would be like A, 0, 0, B, infinity, C, infinity. That's what we're going to start out with. If we don't have our temp prices variable, then for k plus 1, okay, while we explore all the edges here, so these 3 edges, what's going to happen is, so B is going to update to 100, C is going to update to 600, but then if we, since we're looking at all edges, we'll also happen to look at this edge here, and obviously 300 is less than 600, so 300, but this is wrong because we want k equals 0, aka 0 stops. So that's why we need to keep a temporary hash map. So in that case, what would happen if k is 0, it would be like a 0, b would be to 100, and then to c would be 100, okay, or sorry, 600. Okay, and then how we calculate these is we compare. So I should explain how we calculate B and C. So how we calculate B and C would be, so how we calculate B would be this weight, sorry, this price plus this value here in original prices. Okay, and how we calculate C would be this here, 600 plus, A0. And now if we're looking at this last edge here from B to C of 200, what we would be comparing would be B of infinity plus 200. And obviously that's going to be infinity, and we get to keep our little 600 here. And still retain our condition that we have k equals 0 stops. And that's how we're going to do it. Okay, so to code this up, so we're going to have our prices array, our hash table, which is going to be that. And then initially we're going to fill it up with everything except the source airport with the infinity. So for I in range n, if I is equal to source, prices source is going to be equal to 0, else, or sorry, I guess same difference there, else prices source can be equal to infinity. Okay, great. So we have that. And what else are we going to need? Or we're going to need our result, our total price. Actually, we don't really need that either. So I think we can jump straight into going forward algorithm. So for I in range k plus 1. Okay. And then for we're going to explore each edge here. So for from, make it better. So for from to and price in flights. So what's going to happen is if the price starting at from here, from this original table, prices row is equal to float infinity. We're just continue because no matter what we do, infinity plus whatever the price is going to be infinity. Else, what we're going to do, one thing I forgot to do is have my temp prices hash table. And that's going to be equal to prices.copy. Okay. Else, what we're going to do is update temp prices here for the destination. So that is going to be equal to the minimum of prices from plus price and itself. So prices from, like if we're here, 0 plus the price, the weight of this edge here, okay, which would be 100, and then here, which would be infinity in this case. So obviously we're going to update this guy to in 100. And yeah, that's pretty much it. Then I'm going to assign prices to temp prices, updated after this iteration of null and void. And yeah, that's pretty much it. And then what we're going to return is if prices at the destination is equal to float infinity, that means there is no way to reach the destination within the k stops, or is it not possible to reach it at all, then turn -1. Else what we're going to do is turn prices at destination here. Okay, and yeah, that's pretty much it. I'll do a dry run. Oh, sorry, supposed to be colon there, and then indentations off. Oh, that's straight line. Okay. Well, let's try that again. Cool. Let me try all these other test cases here. Great, and I'll try submitting. Awesome. Another way of doing this problem without using the Bellman-Ford algorithm is using breadth first search, BFS. So basically we do BFS traversal, basically k+1 times or until the queue is empty. And yeah, we want to calculate the minimum distance to reach our destination node here. So it's pretty similar, pretty standard to that of BFS. So what I'm going to do first is some setup. So what I'm going to do is twirl, or actually so this is HashMap is going to store the minimum cost so far to get to a node from the source, and I'm going to create my adjacency list here. So what I'm going to do is for I in range n, I'm going to have so I'll fill up my adjacency. I go to empty array so far. Okay. And while I do that, what I'm also going to do is fill up this. So if I is equal to source, then for this at I is going to be equal to 0, else min cost so far at node I would be infinity. Okay, and we're going to decrease this try to decrease this using breadth first search. Okay, now let's properly, so we create an adjacency list. So each node will have empty array so far. So now let's fill up our nodes neighbors. So for from, to, and price in flights, adjacency from the dot append. What I'm going to append is a tuple of 2 and price. Okay, so store a tuple with the destination and the price. Okay, great. So we have those set up, and we can pretty much jump right into breadth first search. So now I'm going to have my breadth first search queue here, and initially it's going to have source and 0. Okay, great. So queue is going to be an array of tuples, and the tuples and tuple format will be the node and the price. Okay, so now let's do queue, the breadth first search. So while the length of q does not equal 0 and k greater than or equal to 0, so we're going to be decrementing k. So what I'm going to do is first create a new queue here. So this will contain all of the queue's elements children, and then later we'll assign q to new queue for next iteration of the breadth first search. And then k minus 1. Okay. And now what I'm going to do is for the node and the price in queue, and I'm going to get nodes children from the adjacency list. So children is going to be equal to adjacency list of node here. Great. And if we've got to remember, so for a child in children, and what I was going to say is for format, a child is going to be a tuple, where it's going to be like node price. Okay, so that's how we store it up here. Got to remember that. Okay, so first what do we want to do? First we want to check, so if child 1 plus the price here is greater than min cost so far at child 0. Okay, so 0 will represent node, 1 price. Okay, so if getting to this node, okay, if getting to a child from this node cost more than the minimum cost so far that we recorded to get from that node to the child, then what we simply want to do is continue. And we want to continue because this will make our runtime faster. So if we don't continue, then we'll be needlessly adding it to our new queue. So in that way we avoid that. So then what we want to do now is min cost so far is going to be equal to child I or 1 plus price. Okay, and then what we're going to do is add this child to our adjacency list. But first, before we want to do that, we want to check if child 0 equals destination, then continue. And why do we continue? Because again, we don't want to add it to our new adjacency or new queue here. Okay, we don't want to explore that destination node in our next iteration of breadth first search. Okay, now finally, what we can do is new queue.append. New queue.append, and then we will append basically the node and the price. So it's going to be child 0 and min cost so far for child 0. Okay, and yeah, finally, after all that, we want to do queue equals new queue. And yeah, that's pretty much it for breadth first search here. So now the return value, so if min cost so far at destination is equal to infinity still, then return -1. That means we can't reach this destination from our source, either because it's impossible or not, it's not within the k-stops. And otherwise, return min cost so far destination. Okay, so let's try running it. Okay, let me use some other test cases. Awesome, I'll submit. Okay, great. And the runtime of this would be similar to that of the other one that you use in Bellman Ford, and it would be O of so it'd be O of I'll just blink it here. It'd be E times K. Okay, E times K because we want to do this at most K times, and E because we're basically exploring kind of each edge in breadth first search here. Okay, yeah, and thanks for watching.